In order to effectively use a spectrophotometer, you should scan across all wavelengths. Doing this will allow you to determine the lambda max for your particular substance. The lambda max refers to the wavelength in which the absorption spectrum of a substance has its highest absorption. In this particular graph, the lambda max would fall around 275 nanometers. Another reason why you should scan across all wavelengths is so that you can compare the absorption range of a substance at each specific wavelength. Comparing the absorption of a substance at various wavelengths can allow you to identify an unknown solution by comparing its absorbance across the same ranges to a known substance's absorbance. Here is the Beer-Lambert law. In this equation, the relationship between concentration and absorbance is directly proportional and positive. The A is the absorbance of the substance and can be found by the absorbance emitted through the spectrophotometer. The E, or epsilon, is the molar extension coefficient and can be found by calculating the slope of the line that represents the relationship between concentration and absorption. The C is the concentration of a substance that is in the cuvette and can be found by using the C1 times V1 equals C2 times V2 formula. The L is the path length of the light in the spectrophotometer. In this case, it is 1 centimeter because that's the distance of light that traveled through the cuvette. It is also important to remember that you must zero your machine with a blank solution before testing the absorbance of various concentrations. Zeroing the spectrophotometer with a blank subtracts the absorbance of the blank from the solution's absorbance. Failing to zero the machine would make our absorbance values higher than they actually are. First, each member of the group carefully transferred some solution from each of the standardized series of dilutions to a clean cuvette using a transfer pipette. We made sure that the solution did not pass the mark indicated on the cuvette. In order to zero out the spectrophotometer, we had to use a blank solution of ammonia. First, we had to clean two sides of the cuvette. Then, we carefully placed the cuvette with the ammonia in the spectrophotometer with the clean sides facing the beam. We closed the lid of the spectrophotometer before scanning the sample. Then, we made sure to hit the zero button to negate the effect of the ammonia in our solutions. Next, we carefully opened the lid, removed the blank cuvette, and then we closed the lid. After zeroing out the spectrophotometer, we were then ready to scan the samples. First, we had to clean two sides of our first diluted sample. Then, we opened the lid and placed the sample in with the clean sides facing the beam. We closed the lid. We scanned the sample and recorded the absorbance in the appropriate spot in our notebook. We again carefully removed the sample from the spectrophotometer and closed the door. Each group member used the spectrophotometer to scan at least one sample, and they recorded the absorbance. We only had to zero the machine once. We scanned and recorded the absorbances for 4 different samples. After we were done using the spectrophotometer to scan our samples and to record the absorbances, we made sure that our area was clean before we left. The notebook shows each of our 4 samples in order from most concentrated to least concentrated. You can also see the absorbance for each sample in nanometers to the right of its concentration. We recorded all significant figures that were provided to us by the spectrophotometer for the absorbance. We also used significant figures to calculate the different concentrations of our samples. Finally, we plotted a graph to show that the concentration is directly proportional to the absorbance in a linear, positive fashion, and thus it satisfies the Beer-Lambert law.